You haven't got any other system. Where does the volume, where does it come out?
Okay, so welcome to Solarchat, everyone. And I'll hand you over to Douglas Smith, and he'll give us hopefully a talk on SHG. We'll enjoy that and we'll have questions at the end.
Yeah.
I'm just a distraction.
Thanks, Alexandra. I think one person still is unmuted. I think it's Solar Gain. Okay, now they're muted. What I thought I'd do is let me just pull up some slides and I'll do a share screen and let's see if that works. Hold on. Okay, let me do share screen. There. Okay, that's not what I want to share. In fact, what I want to share is.
We had a choice of all the microphones.
There we go. So do you see kind of what looks like a PowerPoint presentation in front of you?
Yeah.
Yep. Okay, perfect. So what I wanted to do was go over a little bit. Well, first of all, why would you want to use this technique? It is a little bit more difficult than your typical solar observation technique. But what it does is it can give you a very narrow bandwidth, something probably between maybe 0.2 angstroms and maybe even a bit less, versus a typical maybe 0.5 to 1 angstrom you'd get with other techniques. You also get a very wide field of view. You can do a full disk image, which a lot of techniques, you know, like a quark, for example, you have a very narrow field of view. You can get very high spatial resolution depending on the telescope you use. I think the sweet spot is about a 4-inch refractor, actually. So you're getting around limited by the seeing, so 1 or 2 arc seconds. Of course, you can also look at multiple wavelengths, which is a big plus. It's not limited to just hydrogen alpha or calcium K. You can, in theory, look at any wavelength. And particularly if you go up to, let's say, 4-inch, like a 4-inch hydrogen alpha etalon is going to set you back a lot, obviously. So comparing to a big etalon, it's actually a lot less expensive. So I won't go over all this, but basically I'll do a quick view of the history because it has a sort of interesting ancient history. And I'll talk about some of the data acquisition techniques, actually how to capture the data, and also then how to take the data and create an image, because it has an interesting way of creating the image using modern software. So here on the left, I think is one of the first spectroheliographs, about 1900. And interestingly, it's pretty much a similar instrument even today. Here, I'll just sort of zoom in here, maybe you can see. So the slit is sort of around here. So the telescope, this is a big telescope, focuses the sun's rays here where there's a slit. It goes down to some optics, which is a collimator. Here, there's a grating down here on the bottom left, reflects back up. And in the old way, what they'd have is they have a piece of film, and the film would be scanned across the image that was like reflected. And in this technique, they had this hydraulic pipes that would make everything move in synchrony. And then this is a example of a contemporary one that was built in Paris. I think it's actually more or less still being used, as I understand, the spectroheliograph at Meudon. At least I've seen it referenced. I'm not quite sure if it's the same as it is then, but it's still being used. And what's kind of interesting is that this was the only way at that time to image the sun in the various wavelengths, like hydrogen alpha and calcium K. I think both of these images are in the calcium wavelengths. And you know, have to realize this was taken in, I think this one, it says it was 1897. You know, it's pretty good. And this was in like 1906. Again, it's pretty good. I've put a link up here. I discovered that Pedro, who's active on Solarchat, wrote even like a history of the spectroheliograph. If I click on it, I think it comes up here with a link to it. And, you know, he's written a whole long essay, which I didn't even realize until I started researching for this presentation. So if you're interested, you could find out more by looking at the article that he wrote. Interestingly, I actually just did a little bit of research to figure out when was the first images taken with Fabre-Perot on the Etalon, and I think it was done in 1968 by some Russians, actually in Crimea. You know, the wavelengths, the bandwidth was about what we have today, about 0.7. They even mentioned that if you double stacked it, you'd probably get better bandwidth. But between, let's say, 1900 and 1968, the spectroheliograph was the only way you could take images of the sun in various wavelengths. And I'd say pretty much around this time in the 1970s, the Etalon, you know, it was a bit easier to use and so on. And so the spectroheliograph kind of a bit faded away from use in most cases, both professionally and among amateurs. And then around the year 2000 or 2000, I'd say 2002, it kind of came back to life a little bit, mainly by some guys in France. I'm not going to, you know, attribute every single person, but a guy named Daniel Defourneau started building this instrument, which again, if you compare it to the instrument of Hale in around the year 1900, has the same similar elements. There's a slit here. He made it out of brass, which I think was a common way of doing it. There's a telescope here, which acts as a collimator. There's a diffraction grating, and then there's another lens where he attached a camera. I think actually here it's just an eyepiece. But you can look at his webpage. I put a link here too. It's kind of interesting history. I think he was the first one to use a digital camera. He used a webcam. He created his own software in Visual Basic that did a reconstruction. And he got some pretty good images, actually. This is a hydrogen alpha image. And I'd say it was around this time this technique kind of was revitalized by using some digital technologies and sort of shrinking everything down. He said that his instrument, it weighed about 6 kilograms. You know, these other ones from the turn of the previous century were obviously like tons, I'd say. And he says he could run it at 15 frames a second, I think limited by the computers and the cameras at the time. And he also said he was a bit limited by the slits, which weren't particularly good. He had to grind them by hand. He also, in this way, he didn't scan the slit across the sun except by just the sidereal rate of the sun moving across the slit. And in today, we'd probably scan it at 8 or 16 times that, because we have better cameras and computers and so on. And around 2020, Christian Buhl came up with this really nice design that's very popular today he called it the Solex, or Solar Explorer. I was looking around to see when the first time it was referenced, and I found like this reference like December 1st, 2020, where he showed the design, and it's made out of 3D printed plastic. And again, the results were really good, and it was very small. You could mount it on a small refractor. He and his, I believe, wife, Valerie, developed some software. That's Valerie there. She developed some software which could reconstruct the data and create an image. We can go over that a bit later. So I'd say that was a bit like groundbreaking, the Solex in 2020. It caught on fire in the French astronomical community and has started to become quite popular in other places. I think the key thing is it's you can build it with 3D printing if you have that capability, or you can have a service build it for you. You know, this diagram shows it's again very similar conceptually to what Hale did in 1900. There's a slit here in French font, and then there's a collimating lens. There's a grating. There's another lens for the camera, and it goes on to some sort of digital camera. The reference I found, it weighs 500 grams. I think that's probably just the plastic parts, not with the camera, but nevertheless, it's very light, and you can stick it onto smallish refractors. And maybe I can go over why that's possibly like a limitation, and the results are very good. Here's another variant that Ken Harrison built. He called it the mini SHG in 2021. Again, it looks very much like the Solex. It has here, I'll zoom in a little bit here. It's got the telescope attaches here. This is a 2-inch adapter. He actually used the lenses that are provided from this company called Shellyak, who provides some of the equipment for the Solex. So he took 2 lenses from them, 125 millimeter lenses. It goes to a grating. This grating is actually a little bit bigger than the Solex grating, and then it comes here to the camera. So and the advantage is this is actually a little bit scaled up from the Solex, so you can use a little bit bigger telescope. The issue with the Solex is it's sort of optimized for about a 400 millimeter focal length. And if you use greater than about that, you kind of crop the image and you can't take a full disc actually. So this is a little bit scaled up version. There's some nice images in calcium K that Ken took, get some nice protuberances and filaments and so on, which you can't typically see if you use like a Lund calcium K filter. He says his weighs 1.2 kilograms, which I think includes all the cameras and things like that. That sounds about right. He built it out of MDF, which is a kind of a thin wood. And he is using a Skywatcher 80 ED. So it's an 80 millimeter aperture, 600 focal length. And with this arrangement, you can do a full disc. What I did was in 2020 and 2021, I built one out of foam board and glue. This was my first version here. And then on the right is my sort of second version. And I might actually, hold on one second. I'll actually stop the slideshow for a second. I'll stop the share, and I'll actually, so it looks like that. I don't know if, can you see me here? So that's what it looks like. You can take off the top and you can see the sort of elements like here. Here's where the telescope attaches to, the light comes in, it bounces off a diffraction grating and goes into another lens here where the camera's attached. And in my version, there's a little like screw here on the back, which you can use to rotate the grating to look at different wavelengths. So on this, I think I weighted, it's about 1.5 kilograms or so with all the cameras and the attachment stuff. So small, and I didn't have a 3D printer, and I'm not very good at working with wood, so I just use foam board.
Douglas,
Yes.
what do you use for gluing a foam board?
I use just normal glue and hot glue gun. You know, there's this white glue, white kind of glue. If you want to sandwich sheets together, I'd use the white glue. I forget what it's called, but you know, the sort of whitish glue you can buy from arts and crafts stores. And if you want to glue like edges together, I just use hot glue, you know, these hot glue guns, and works really well.
Thank you very much.
Yeah. Let me go back to the share. Share screen. Okay, so yeah, I calculated as 1.3 kilograms in my case. So at first, as you see here on the right, I was actually using a kind of short slit. And what happened with a longer focal length telescope, I could only take about half the sun. which isn't bad. You can take, you know, half the sun or a third even and stitch things together. But I decided I'd really like to do the whole sun. And at that point, you have to think of what's limiting the size. Well, the camera, for one thing, you have to have a big enough camera, of course. You have to have appropriate choice of the optics, because there's either some magnification or demagnification based on your choice of lenses. But the main thing is actually the slit and how long the slit is. So I thought a little bit about the slit issue. What I was actually using at first was a slit from Thor Labs, which makes these slits, which are mainly used for laser optics and things, and they're only 3 millimeters long, so quite short, and like 10 microns seems to be about the right kind of length. The typical Solex uses this slit made by Sheliak, and that's 4.5 millimeters long, which, as I said, can get you about a full disc at 400 of the millimeter focal length. And again, their standard is 10 microns. Seems to be about like a good width. But I thought about it also. The Sheliak one is made of glass. The Thor Labs one is made of stainless steel. I decided that probably the best material was what's called fused quartz, because it has a very low thermal expansion coefficient. So you can have a lot of solar radiation impinging on it and it won't crack. Like I've never cracked a fused quartz, even with a big refractor. While I know that people who've used the Sheliak slits, if they don't take precautions, this piece of glass will just crack under the heat. Here's an example of when you make these slits photolithographically, they're pretty perfect. I think the Sheliak one is also perfect. The ones I had made also were perfect. This is 9 microns wide. This is an example of a Thor Labs slit. You can see it's created by like laser cutting this piece of stainless steel, and they're kind of rough, and these defects create defects in the image as well. So I won't go too much into it, but I had like one wafer made, which had 49 the pieces on it that looked like this, and then I mounted them on some copper discs to dissipate whatever heat, and then you can mount it in various things, like a Thor Labs tube or a filter cell. And I think I've sold about half of the 49 that I had made to various people around the world, including Brian Martin, and I can show some other examples too. Ken Harrison actually also bought one or two, so his images are also made with these quartz ones. So Ken Harrison also made this very nice spreadsheet, which I helped him with recently to sort of beautify it slightly, called SimSpec, where it gives you an idea of the image scale if you know the telescope you want to use. Usually people use just what they have, and then you can kind of work around what sort of optics you want in terms of magnifying or demagnifying, you know, your slit. It sort of tells you as well how many frames you need, how fast you need to scan, and so on. I won't go through it all, but it helps you a lot to sort of figure out a lot of the parameters when you're first starting out. So that's very useful. And I just mentioned here on the top, assuming you want around 1 or 2 arc seconds per pixel, you're talking about, let's say, you want a kind of region of interest, which is about 2,400 pixels long, which is a kind of reasonable size for a lot of these cameras, like the 178 mm, which seems to be the camera most people use. Here's an example of a screenshot, actually taking some data in hydrogen alpha. I used fire capture. A lot of people use sharp cap. So what this is this ROI, which I mentioned. This is actually taken with a bigger camera, 183 mm. So it's actually 3,300 pixels wide, and 150 tall. You could do a little bit smaller, like 100 if you're careful. So what you see is this is the spectral line of hydrogen alpha, and all the data is actually in this line. All the data in the image is actually in this one line, all this white and dark areas. For scanning, I have a Skywatcher mount, a HEQ 5 Pro, and I use EQ mod, so I can just control it electronically rather than using a hand controller. But you can set your scan speed here like 14 times or 12 times or 16 times sidereal rate, and then you scan either east or west or north and south depending on the orientation of your instrument. Here's an example of what it looks like. This top one is calcium K. It's a kind of broader line and also has much higher contrast. So you typically have to do an exposure so you don't saturate. You have to make it look a bit darker in order not to saturate the bright areas. This bottom one is calcium H. It's a little bit narrower than the calcium K. And a lot of people who do this use calcium H because it's a little bit brighter. So there's more photons, and it's also a little bit narrower, which helps too. So that's what you're looking at when you take an image and you scan. And I'll just show you here on the next page. So like this is actually a slowed down scan. So you can see it, you start off the sun on a limb, a bit off the limb, and you sort of scan it over it. And so then the image starts to look bigger as you get to the middle of the sun. So this is around the middle of the sun. And all these little wiggles here, this is hydrogen alpha. All the little wiggles are the data that create the image. So one of the challenges is focusing. And the object is you want as many wiggles as possible, because the more wiggles you have, and it sounds a bit silly, but the more wiggles you have, the more data you have. So focusing is the hardest thing because you actually have 3 lenses in theory to focus. But actually the hardest one to focus is a telescope. And so what you want is, here, let me just stop this. So here we're going all the way to the end. So, but now we've done a full scan. I think this is slowed down maybe about 4 times. But if you look here, you can see a couple of interesting features. So I just made a point here. If you go to like, where is it? 42 seconds. Right here is a sunspot. So what the meaning of this is in this X direction, it's a spatial direction. And in the Y direction is actually a wavelength direction. So a sunspot is black in all wavelengths, is what this is saying. So you can see this big black vertical line is a sunspot. If you look at, here's another little interesting feature I found on this one. Right around here, you can see there's a little loopy thing that's going on. Just sort of zoom in. So like this is some sort of flare. And so this is a Doppler shift. In this image, blue is up. So if you go more up, it's bluer. These lines always curve so that it curves up towards the blue. So this means there's some little flare thing that's sort of headed towards us because it's a little bit blue shifted, which is kind of interesting. And then I wanted to show one more little feature at 580. I just marked it down. Hold it right around. Okay, here we go. So if you look at this, you see this little tiny line, that's a speck of dust on the slit. So that's this little line, they call it, I don't know who invented this word, transversalium. So that little speck of dust causes a very, very narrow vertical line, but that's constant. as you scan, so it doesn't change. And that can cause a kind of black line in the image. And so using software, we tend to just remove those. But I mention this because if you can see the transversalium, it means you're actually in good focus. Like, so if you can see the spectral lines are sharp in like this X direction, and you can see a few transversalium in the Y direction, that means that the collimator and the camera lens are in focus. And then you just have to work on getting all your little adjustments on the telescope right. So you can, for example, you can start focusing just on the limb there. So that's a limb, so you can make sure the edges are sharp. And then you can tweak a little more and try to make all the little wiggles in the spectral line sharp. And if you look, like I won't go into it too much, but if you see just on this particular image, if you go to the very end, you can start to see there's a few, there's some, you see that's actually, there's actually some prominences at the very, very top of the image. And so these little things here are actually some prominences coming out the very, very top of the image. So let me go on now to explain how to make the final image from the data. So what you get is you get a video file, usually an SCR file, but you could actually do an AVI file too, and you use some software. The software that's probably most used is one from Valerie, who created this one that she called Inti, and she has a website for it here. It explains a little bit how to use it, and you can download it. There's a Windows download, or you can actually download the original Python source code if you prefer. Meaning my son and I, we took her original code, a very, very early version of her code, and we created our own version. And then for a while, Valerie and I were swapping code. She took some of our code and we took some of her code. Sort of in the meantime, over the last year or two, they've diverged a little bit. And she's put some bells and whistles for things that she and Christian think are important. And we put, meaning my son and I, we put stuff and features in which we wanted. But they both work and they give pretty similar results. And I'd say most people use one of those two versions of the software. They both have sort of similar like interfaces, I'd say. This is a sort of Python GUI. And let me just explain a little bit what's being done. So what Valerie did, which is kind of a nice concept, is she had this idea. If you take all the frames in the image and average them, you get a sort of maybe kind of blurry image which has no features. And so that's the average shape of the spectral line. Again, it's a little bit curved. Also, this is a bit magnified in the X direction. And then you then fit with a polynomial what the shape of that spectral line is. In theory, it should be parabolic. We actually use a cubic. I think she uses a parabola. But then you fit this line and you try to find the center of that line, usually the darkest part of that line, and you say, that's the part where I want to sample the data. And then you sample the data on that line in the middle using this polynomial fit on every single frame. And then, typically your image in the data won't be exactly a sphere. It'll be maybe an oval of some sort. It could even be slightly tilted if everything's not quite right. You then detect the edges, and then you force the image to be a circle, which is what we want. And then you come up with this, what in Valerie's terms she called the YX ratio. If the YX ratio is greater than 1, it means your original image is too tall and you want to stretch it and so on. And then there could be a rotation. In this case, there's not much rotation. She calls it some sort of angle. We call it like an unrotation angle because we have a different algorithm for doing it. but it gets to more or less the same place. I mean, this one isn't rotated much. It has an unrotation angle of about 0.3 degrees. You generally want, if possible, to be at a degree or less. And then it goes and calculates, and then there's this nice algorithm called CLAHE, which I never had heard before. I started this, contrast limited adaptive histogram equalization. Apparently it's used for CT scans and X-ray scans to make things more visible. And like, this is actually the raw data as it comes out of the program. It's actually amazingly good. That's a single image. And then the program will also put like a black disk on it, and you can see prominences. It's a good test to see if the circularization is correct. And also it's a good test just to see if there are prominences. Although actually, usually this CLAHE image is what I always use, because all the prominences are there too if you bring them out, you know, with levels adjustment and so on. So I never actually use this black disk image. I just use the CLAHE image, which is usually captured in 14 or 16 bits, which is I think sufficient. What I thought I'd do here is I just show you how it works, because it's kind of amazing. I don't know if anyone's ever, I mean, some people here have done it, but it's kind of amazing when you first see it actually, the data capture or recreated from the file. So here, if I click on this, it'll call up the program. This is our program, not Valerie's version. So it pulls up this little console window. I guess it's thinking for a second. Okay, and then here's the GUI. There's actually a way you can run it from a command line if you so choose. You open, you choose a file. You can. I have some example files here. So here's an H-alpha file. There's a little toggle here to show graphics or not show graphics. Normally you'd run it not showing graphics, but the show graphics is kind of cool. It's like a demo teaching thing. You know, depending on how you orient your acquisition, your SHG, you might have to rotate things, depending if you're scanning an RA or DEC. And in our version, there's a little slider for the amount of the transversalium you want to remove. But Valerie's works at a level 3, and I found actually 3 is a little high. You probably want a little bit lower. But anyway, so then you push the button, and the program reads the file. Okay, in this case, there's 4,659 frames, quite a bit. It creates this average line, and now it takes that line or that polynomial and starts to reconstruct across the data frame by frame. And then here's the image. It kind of pops out, and it's kind of like, wow, the first time you see it, it's like kind of like magic, from this little file, which is just data. It creates that, and then it crunches a little bit on the data to circularize it. And then here, this is like circularized image in hydrogen alpha. It creates a sort of higher contrast version, which sometimes is helpful if your image is low contrast, and it creates this black disk image. And if you push any key, it stops. Maybe we'll just do one more because it's kind of cool to see it. We'll do let's do hydrogen beta. Usually hydrogen beta, it's also kind of pretty. So it's a narrower line than hydrogen alpha, as you can see. And there we go, it's scanning. You can see this one, I actually didn't do a very good job of orienting it. So it's like it's sort of egg-shaped and rotated. But the software will correct for the geometric problems and makes a nice disk. And as I said, the high contrast version is good on low contrast images, like for example, H beta. And there we go. So quite often, normally you'd want to run it without this graphics, because actually the graphics slow it down a lot. So if you were to run it like here, we'll just run this file with the graphics off, and then you can just look at the console and you can see how fast it actually processes. Okay, now it started, it's reading the frames. I think takes about 5 times less time if you don't have the graphics on. Okay, so now it's found the polynomial, it's figured out the rotation, and now it's done. So it's written the files to the disk. As I said, it's about like 4 or 5 times faster if you don't have the graphics on. And you can do it as a batch too. Like if you wanted to select, you could select, all the files and do them all at once. In which case, you certainly want to do it with the graphics off to save time.
Douglas, hi, Stuart here.
Yep.
Just a quick question. So this works on full disk images.
Mm-hmm.
What if you're just zooming in, so you got this, well, you haven't got the full disk data, as it were. It's going to struggle to normalize the image, get it the right ratio and everything.
You need, let me just, you need to have some of the limbs showing, but you don't need the full disk. So if you have a quarter or a third, maybe, you can certainly do it that way. I know people who, because their slit is very small, but their focal length is long, like over a meter maybe. So like, let's say they're using the traditional Solex, which can only really view about a maximum of about 420 focal length, but they're using maybe 1200 millimeter focal length. So they scan maybe three times, and the software will accommodate that, and then they stitch it together. So as I said, something about a third will work fine, but you have to take it end to end so the software can see the limbs on the left and the right.
Okay, right. Yeah. Just another quick question, if I may.
Mm-hmm.
The image that was rotated, sort of egg shape and rotated, is that because the slit wasn't aligned with the scan direction? I mean, how does that work?
Yeah, that's right. That was I actually deliberately put that in there. It was actually, hold it. I'll just turn off the share screen for a second because it's kind of funny not to see you. Yeah. So the I was trying out a new telescope and so on, and so the SHG was actually slightly tilted a bit. It wasn't quite along the direction. It has to be either this either has to be perpendicular to the RA or the deck axis, and I was just a few degrees off. It was about 4 degrees off actually, but 4 degrees is noticeable. But by eye, I found you can get to within a degree, and within a degree is fine.
Okay. Yeah, that's interesting. Thank you.
Let me turn back because I'm almost done with the slides, I'd say. Here, let me turn that off, close that. As I said, what you're left with, by the way, I'll show this. Let me see. I think this works. This is actually the folder where I just wrote all the files that we were talking about. So, like this is this. Here's this H alpha version, and then there's this high contrast version, and then there's this one with a black disk, and there's this is this like picture that I showed before, which shows this is the uncorrected image. Here's the uncorrected image for H beta, which is this sort of egg shape, slightly rotated. This is the calcium H, which was actually pretty circular. I should mention one of the differences between how Valerie does it and how we do it is we actually look a little bit off the center of the spectral line, because the spectral line, as you can see here, it's quite dark, And so it's very hard to do edge detection when it's like the blackness of space and a dark line. So what we do is we actually measure shifted by 10 pixels. So we're actually measuring the line like a little bit where there's more contrast, basically. And so that's why, like here, you can see this doesn't actually look like hydrogen alpha. It's a shifted away from the center of the spectral line, hydrogen alpha, which is in itself interesting. But we have a little bit less error, I'd say, in terms of detecting the edge because we have that little trick we use. Also, there's this graph here, which is here. I'll show you this one. This is the transversalium correction graph, which shows you how much how much dust basically is on your slit. And actually, this is kind of a little bit useful because if you have this very narrow spikes here, it means actually that your focus is really good. So it's kind of a way to see, oh, if I see these very narrow spikes, it means that everything's actually working quite well. Here's the same data I ran using Valerie's program. Yeah, it's pretty much the same. Here's the like hydrogen alpha. I kind of rotated it so it's the same sense. She also doesn't crop it square. Like we have this system where you can crop it square. So in case you scan too far, you actually just crop out all the black parts on the top and bottom. A little bit hard to see here, but she has a bit of a different way of doing geometric correction. Let me see if I can find a place. Okay, see what she does is actually she does a distortion, like a linear stretching and a rotation. So you can sort of see here, like you can actually see that there is a rotation. The problem with that is that this sort of transformation is a little bit hard for stacking software to accommodate because all the pictures can be slightly rotated and be slightly different sizes too. And so we have a transformation which is a pure shear transformation, which it turns out stacking software works a little bit better. I noticed her black spot sometimes has a little bit of a problem too, but I don't think that's a big issue. For the most part, the images are pretty much the same. Okay, so let's go to the next thing. This is actually what I'm saying, that there's a lot of data there that we're not even using because we're only looking at the center of the line. If you look off the line, and so this is an animation where we're kind of taking a sequence of images, what I call pixel shifted. So going from, let's say, blue to red across the spectral line. This is the center here. I'll just go a little faster. So the center is right here. And then if you go to the left and right, you can see that it's a little bit blue and a little bit red. And the image is different. You can see a few things like some like Doppler type features, some sort of flare going on here, which you could do some analysis on. You can even see a little bit of an effect of rotation of the sun too. So there's a Doppler shift due to rotation. But there's a lot of data there that you can spend some time analyzing if you want to. It's just not the center of the line. You could actually look off the line as well. What I want to do, I've only got a few more slides, but what I wanted to say is that stacking, even if it's a small number of frames, like 5 to 10 frames, 5, 6, 7 frames, can really improve the image. So you can take a whole series of scans. Down here you can see just a whole bunch of scans. I'll just zoom in here. Series of scans like left to right, left to right. There's a feature in our software where we do like a mirror flip so you can get them all going the same way. Then you just throw them all into the stacking program, and generally you choose like the number of frames you want to stack. So the total frame here was 20, and okay, I chose like the best 11. Usually I just let the program decide what the best 11 is. Though I eliminate the ones that are really bad. And then you get some really high quality images. So like for example, this is a stack. I can't remember how many it is, but you know, you get, it eliminates all the little noise on the edge, amazingly, and you can really get some good spatial resolution. Just show a few. That was hydrogen alpha. This is calcium H. You can start to see some nice structures and all sorts that look very smooth. Maybe just show one more. Okay, here's a kind of recent one. This is hydrogen alpha as well. I'll show one more, which is a comparison: hydrogen beta and hydrogen alpha. Hydrogen beta on the left, and hydrogen alpha on the right. And again, it's not stacking many frames. It's stacking, you know, on the order of 7 or 8 frames, and it really helps the noise. I'll just show you how it works. So, for example, this is here. That's one frame, and so these are actually real raw data. You can see they're all like a little bit different. Some have a little bit of noise. Some are better than others. This one looks like it has a bit of clouds or something in the way. So we just take those, which are pretty good, but then we throw it into the stacking software. And so this is what comes out. This is just as it comes out of stacking software. You can see it kind of cleans up some of the irregularities. And then once you stack, you can, of course, then sharpen. So this is, I put it into like IMPPG, this great program, and then it can really sharpen things up a bit. And then you can put it into some processor. I use Photoshop Elements, and you can play with the levels, and you can you know, bring out prominences and so on, which are all there. Like you don't have to actually put, you know, like 2 images together to get the prominences. They're just they're all there in the data. So that's sort of how you do the stacking. Let me just show you here. I have some links here to the particular the piece of equipment. This is my main instrument. This is like a 4-inch refractor, 106 millimeter like aperture. It's 720 millimeter focal length. Here's where the spectrometer is, and the rest of it's pretty kind of a normal telescope. Here's a close-up of what it looks like under the hood, under the box. So there's the slit is actually right there. This is just a normal, you know, Pentax camera lens, which I've found worked pretty well. It goes to the diffraction grating. It goes into another Pentax camera lens, and then this is the camera here. I just use the helical focusers built in to the camera lens because they're quite nice. And what's actually really nice, if possible, is to use an electronic focuser on the telescope. These ones you can do manually, but it's really tricky to adjust the telescope focus unless you have an electronic focuser, I found. And let me just show you here. This is a nice little video I made of, this is sort of the view of my balcony where I do most of my observing. So you can sort of see how it's laid out. This is with the sort of cover on the spectrometer part, blocks out the light. There's actually one little piece of the cover that's not on there, just to show the camera. And so this is with the box off, so you can sort of see the optics. It's not very complicated, and you can sort of see it's not like super expensive stuff either. The reason I built it this way is because if your spectrometer gets kind of big, it puts a lot of weight on the telescope focuser, and there can be some bending and some issues with focusing. So what I did was I tried to think of a way to like minimize the weight on the focuser. So what you can see here is basically everything is on this dovetail. So the only torque on the telescope focuser is actually this one lens, which is kind of modest, but all this other stuff then is attached to the telescope dovetail itself rather than weighing on the telescope focuser. But I can show you like another way of doing it too. Someone just sent me some like nice version that he's built recently. So suggestive components I found, as I said, on this telescope works pretty well. This is what Ken Harrison uses, this like EvoStar 80 ED. I actually bought one recently too. Works really well. It's 600 millimeter focal length. It's f7.5. Around f7 I find is pretty good. A lot of people use as well something like about a 100 millimeter f7. There's a whole bunch of people that make refractors like this. And I'd say this 100 millimeter aperture is kind of really a sweet spot. You get really good spatial resolution, and they're not super expensive, and you really only need a doublet. You don't really need a triplet. I mean, I have a triplet on mine, but I don't think it's necessary for this like purpose. About a 30 millimeter square grating seems to be quite okay. Again, they're about, in the UK, about 190 pounds. This 178 mm type camera, of which there's a couple of companies that make them, they're about $300 or so. And then there's a bunch of different ways you can build the optics. I've used these Pentax type camera lenses. I've also used like macro lenses or larger lenses, or you could actually just buy lenses from Thor Labs as well. Actually, this is an example of the of this 80 ED, which is really quite a nice telescope. This is with my foam board one. And I mentioned about this tilting. The easiest way to orient is you just point it like in the home position, like celestial north, so to speak. And then you just adjust the sides of the spectrometer so they're vertical or horizontal. Depends if you want to scan an RA or DEC. This one is scanning an RA. And amazingly, you can get to within half a degree just by eye. It's amazing how good the eye is at judging angles. If you do it this way, you don't have to fiddle around with the orientation pointed towards the sun. If you're trying to fiddle around pointed towards the sun and correct angles, it'll take you a long time, and something will probably go plunk on the floor. So there we go. Here's an example of one of the first ones I did using this 80 ED. I mean, the resolution is not quite as high as with 100 millimeter, of course, but it's still pretty good. This is hydrogen beta, hydrogen alpha. And those are my slides. I can recommend some of these books here that Ken Harrison wrote. They're really good on theory, particularly this last one. He calls it Imaging Sunlight Using a Digital Spectroheliograph. It was written, I think, about 2016, 2017. And I contributed like a little bit to it, as well as a few other Solarchat members. You can buy it on Amazon if you want. It's still available, and it's a good reference in terms of the theory of how it works. Christian Buell has a YouTube channel which is really good. Let me see. I can't remember what it's called, but you can find it. It's got some really nice videos about how to build things and how to measure things. Some of them are in English. Most of them are in French. But you can use Google Translate or something if you don't understand the French so well. And I just wanted to mention one more thing. Hold on a second. Yeah, I can't see if I. Yeah, here, let me see. I'll click on this link here. This is a guy named Maurice Valimberti from Melbourne, Australia, and he sent me this. He sent me in the last week. This is his telescope, his spectroheliograph he built in the last few months. It's kind of impressive. So he used 100 mm aperture f9. So it's a pretty big telescope because that's what he had around. And he folded it with these two diagonals. So again, there's not much weight on the telescope focuser because this is actually free to move. And then he used camera lenses. Again, he bought a slit for me, and I gave him some help along the way. He's a very trained machinist. As you can see, he has his own gigantic lathe in the background. And this is how he built it. There's a little thing here where the grating goes. I think he built this in about 2 months, but as I said, he's a very skilled machinist, I can see. This is where the grating is. Here you can see like this is actually, as I mentioned, separated from the rest of it. This is where the slit would go. This is like a dummy right now. He built this really nice thing to hold the grating with a telescope rotating focuser thing, so you get some very precise rotation. And that's one of his first images he took using this. That's calcium K, again calcium K, hydrogen alpha, hydrogen alpha, hydrogen beta, hydrogen beta. I'd say it's very comparable to like images I've taken, which isn't surprising because the aperture is about the same, the camera is the same, and the slit's the same. And he's also using the same lenses that I use, these Pentax lenses. So not surprising. His is probably of comparable quality, I'd say. So anyway, that's my presentation. Maybe Brian's here. Brian has some experience in this. Let me turn off my screen share. And maybe he can also share some of his experiences.
Oh, thanks, Doug. First of all, I'd like a big thanks to Doug because he's been a tremendous help, not only to me, but to a lot of people on the Solex chat group. This is, I just took this out of the observatory. So here's the next version of Solex. And it's really in many ways similar to Solex, just quite a bit bigger. So the total weight of this with the camera is about 1.8 kilograms. And it's all 3D printed in a combination of PETG and PLA. I haven't had decent weather yet to really get good images with it. I've got some passable images. Nice thing about this is it goes on a 700 millimeter 4-inch scope. And I found even with the 178, I can get a full image. I'm using one of Doug's slits. I actually use Doug's slits on both the Solex. I replaced the original slit with the quartz slit, and it works wonderfully. I had to filter the original slit quite a bit to prevent cracking, and I just wasn't happy with the throughput. But when I went to Doug's slit, it's not only a 12 mil, I think it's 12 millimeters, Doug. The
12 millimeter long, yeah.
Yeah, and I have no trouble getting enough light for the system now. So I'm looking forward to a little bit more work with the larger version. I'm using 150 millimeter SI Pentax lenses, Super Takumars, and a 30 millimeter squared grating. It was quite easy to construct. It was quite easy to just set it to do it in PLA and PETG. So I had a double stacked Coronado 60 millimeter system for a number of years and was never just really blown away by the images it was producing. It produced good images, and I sold it and kind of regretted it and was in the process of thinking of maybe going to a Lund when I came across the Solex page and built a Solex, and it was just absolutely amazing. For about 1/10 the cost, I now have an instrument that I just recently did some H beta and some H alpha imaging this weekend with the Solex. Yeah, I can't say enough good things about it. It's a really amazing tool. And it's yeah, if you factor in the cost of a Quark or a large Lund and working in a number of band passes, it's about a 10-to-1 ratio in terms of cost. And I think quality is certainly comparable. Doug's images are, yeah, as you can see, they're amazing. And so anyways, I'd be happy to any questions. I do have some sample images, but I'm not sure if it's necessary to show them. They don't compete with Doug's yet, but I'm working on it. So any questions about building one of these?
Yeah, Brian, just real quick, I just posted on the chat. Are your 3D print plans on Thingiverse or something similar where we could download them?
Yeah, I should do that. I have to warn you, I'm not an expert at this. So I did it all in FreeCAD.
Okay,
And maybe if there's some way that we can just share email, it might be the simplest way. And I could just send you my, so I don't know, Alexander, if that's something that as host or Doug as host, you're able to facilitate, but I'd be happy to share my STL files or
yeah,
my
you don't have,
FreeCAD files.
that's, I mean, you don't have to, and most people don't share their original design. They just share the STLs and say somebody can download it and print. They don't, most people they keep their original design files.
Maybe what I could do is I could put them on the Solex site.
Oh, that's a good idea too.
Yeah.
I was just saying, I don't know if I'll ever have a chance to do this, but it'd be nice if I did.
I'd be more than happy to also supply the FreeCAD files because, as I say, they could probably be improved.
Well, so that's another side benefit. So some people even just use GitHub. So it's whatever's easier.
Yeah.
I see that Matt Constantine's here too, who's has a whole different project that he's working on using spectroheliograph. I don't know if you want to mention just a couple of words about what you're up to.
Yeah, sorry for joining late. We've got a old 1930s style spectrohelioscope that we've installed at Stellafane here in Vermont in the US. And we've essentially turned it into a spectroheliograph by working sort of the same principle and then with same camera principle and then running the resulting images through essentially Doug's software and Valerie's software, which I had made a version that had some tweaks in it because in the case of our instrument, our telescope has got a focal length of 18 feet, and the collimating mirrors have focal lengths of 13 feet. And so you can imagine, we're dealing with sort of partial scans. Our solar image is 2 inches essentially at the focal plane. And so the challenge for us has been adapting the software to work with these partial scans and then stitching things together. But the work that Doug and Andrew have done is just amazing. And after a while, I decided I'll just going to work with whatever their version of the code is. That said, I've been working on sort of a mini spectroheliograph along the Solex plans, which has been assembled but not hooked up yet. One thing that's a little different is this element in here that I replaced with a design that came off of Thingiverse for a helical focuser. And I had to change it, go in and slice some things out so it could sort of fit into the mate with the pre-existing parts. But then what this allows, and I have not had a chance to field test it yet, but this should allow a better tuning between the collimating lens and the slit. This is a helical focuser over here for the ZWO, so that part's fine. And presumably I'd be able to work with the telescope focusing on the slit. The remaining challenge was being able to adjust the focus, focal point, the focal distance in here without having to take the thing apart every time I needed to make a tweak. So, so that's one additional thing I've ginned up, and hopefully we'll see if it works. So those are the two related projects I'm working on.
Yeah, Matt helped a lot in the early stages of the software development. He had some good suggestions and contributed some very useful code. I see there's someone in the Zoom called Christian, but I wonder if it's Christian Buell or not, or is it is it some other Christian?
Oh, Doug, this is John Palladini in New York.
Hi,
How are you?
I'm okay.
Listen, I have a question. Can you talk a little bit more about how you do the scans? I mean, you do rapid scans back and forth, and then that's how you stack them? Because I've been doing Earth scans, and they're very slow and
Yeah, they're
take
very
long.
slow. I mean, you can do it depends on I'd say on your mount, right? Like some mounts take to scanning and some mounts don't take to scanning, right? I found.
Yeah, you have like a speed up thing that you have to make sure, or else you're gonna get a lopsided sun unless it's at low
Yeah,
consistent.
I mean, um, generally speaking, I'd say for the kind of ROI we're talking about, let's say like 3,000 pixels by maybe 100 pixels, these ZWO cameras can do around 300 frames per second, let's say. You know, you have to have an exposure time short enough to be able to accommodate that. And then you're talking about then if you're looking to get about as many frames as the sun is, you know, tall, like then you're looking perhaps like around 2,500 frames or 3,000 frames. Then using actually the spreadsheet of Ken Harrison's, you can sort of see what the scan rate should be. It generally comes out to be something like 10 times sidereal rate or to 20, you know, that kind of range. So if you're scanning at 1 time sidereal rate, right, which is what happens if you're just letting the sun move across the slit, yeah, that's pretty slow.
I
During
could
that
probably go up
time,
to 8.
Hmm?
I could probably go up to 8 times.
If you just use a hand controller, you know, they usually are in increments factors of 2, right? Like 8, 16,
Right.
something
4,
like
8.
that. Yeah, 4, 8, 16, etc. I think beyond 16, it jumps up to like 120 or something. But anyway, but you know, if you target 8 or 16, you know, that's great. You can adjust the exposure time accordingly to get to the frame rate that fits. So you get to, you know, more or less a 1-to-1, this Y over X ratio being 1. It's not too difficult. But as I said, if you have some other way to control the mount where you can get a bit finer control, like EQ mod, you can, you know, do 13 times. And there's other mounts that have their own proprietary software that lets you control it. And I think you can also control the mount from SharpCap. Like that's one of the things I noticed. Some people, if you use SharpCap, there's a built-in controller too that I think you can modify to get any scan rate you want.
That's good. I have one more question and then I'm done. And this whole thing with the helium D3 processing. It seems to be a big secret in the community. Everyone who figures it out that they don't like to share the information on how it's done.
Yeah, that's really hard. I'm not even sure if I did it the best way, but I watched one of Christian Buell's videos, which was in French. I mean, I can understand French, but the trick he showed was the following, basically, just to summarize it, is you take an image near the sodium doublet. The thing is, the helium line is actually an emission line. It's not an absorption line, right?
Correct.
So you don't see it as a black line,
Right.
right?
Flash.
It's like it's like a flash. And so the software needs a black line in order to find the polynomial fit. So the way that Christian mentioned it, and you know, maybe there's other ways of doing it, is you take a very wide ROI that incorporates one of the sodium lines, let's say, and where helium is. Okay, where is helium? Well, it turns out if you kind of shrink things down, you'll find it by the little flash on the edges, you know.
Correct.
But you only see it when the scan is really, really quite narrow towards the solar
The
limb.
edge.
Yeah, the edge. So you make an ROI that incorporates, let's say, one of the sodium lines and this area where the helium is. And then the trick is you have to figure out how many pixels away the helium line is from the sodium line. And then you use the software. I think actually in Valerie's software, she uses something, there's a thing called, I think, free line or something. Basically what you do is you use this pixel shift idea and you put in a number, I don't know, like 115 pixels, and this gets you to where the helium is from the sodium line, right? It's kind of convoluted way of doing things, but I
Can
think
you write software to do something like that?
that would be good. Maybe Valerie's done something. I'll have to ask her if she's figured out a more like easy way
Because
to
it's
do it.
basically, it's called a shallow line, like processing, I think they call it. Because it's not like these nice deep dark lines.
Oh,
It's very thin. It's very.
I think I lost you there, John.
No, it's like very thin. You don't really. It's hard to do. In essence, you're saying doing it by hand. That's basically it.
It's kind of like doing it by hand, as far as I know. But I don't know. Is there anyone else who's tried helium? It's I've tried it once or twice, but it was so much work I didn't do it again.
Okay.
Brian, did you ever try helium? No.
Doug, I think I played around with one of the videos that had been posted at one point, and I might have some code I could share.
Okay.
It would be nice if somebody could put up some files and examples so you could play around with it with the software. And then once you learn all that by hand, once you get it through your blood, so to speak, then you could go out and because if you try to do it all at one time, it's a lot of stuff to try to do all at once and to understand.
Yeah.
It'd be nice if they had a couple of files up there and then you could just download them and then play with the software until you get it right.
Yeah.
You know?
Yeah.
So I just wanted to show my system that this uses a slit from Douglas. And also wanted to show that I made a modification on my Solax. I had the ZWO helical focuser, but I also didn't like the way that the Christian Bull design works. So I got a helical focuser for the telescope end, for the slit end. And this was just a cheapy one that I found on eBay for about $30, which works pretty well. So, and thank you, Douglas, for the slit. It works quite well. I'm really quite happy with the system.
That's great. And so your second helical focuser is for the collimator?
Yes.
Okay. Yeah.
This one's for the this one's for the I was getting mixed up. This is for the camera end, and then this one is for the collimator attached to the telescope.
Yeah. Yeah. I found the problem with the helical focuser on the collimator is it's under a fair amount of torque, right?
That's true.
And so you have to be a little bit careful about turning it.
Yeah.
They don't always turn very smoothly when they're under that sideways torque.
I did have a bit of that problem, and I find that I have to torque things down a little bit so that the whole system doesn't counter rotate out of alignment. But I will work through that.
One thing that I've done, Doug and Richard, is on this new one that I've designed, the collimator is actually floating. So there's a collar here that basically attaches to the telescope, and then the collimator is resting. It's not a friction fit. It's not sloppy, but it's enough that it's essentially floating. And then I just made a very, very simple helical focuser, just printed it. So I can just, I can sort of tweak the focus, but there's no torque or anything on the collimator itself.
Oh, okay. Yeah. I think that's one of the things that can happen is that if you aren't careful, bad things can happen at that collimator junction.
Bad things happened the first time I tried this because very stupidly I had printed nozzle to hold it to the telescope, and it promptly snapped in half as I was positioning it, and the whole system fell 4 feet to the floor. And luckily, it's a wooden floor, and the amazing thing is the collimation was still bang on, and nothing changed. I got lucky.
Yeah.
But, yeah. So that's when I went to this other design and made sure there's no tension on the collimator at all.
Yeah. One thing I found, one other good reason to have an electronic focuser is it prevents the case of the whole focuser just sliding down. If the telescope's pointed pretty vertically, there's I mean, most focusers won't hold unless the screw is turned in. But then you can't focus if the screw's turned in. So if you're doing manual focus, you have to be pretty careful about something bad not happening.
Yeah.
So the electronic focusers, they sort of lock in place when they move. So they'll move, and then you don't have to worry about anything slipping.
Indeed. Yeah.
Well, I found that the advantage of having a electronic focuser was that I could set up the system. If I tried to look at the monitor screen out in sunlight out on my driveway, I couldn't really focus very well. But with a electronic focuser, I can go back to my so-called warm room, or actually my office, and then in a darkened room, now I can get the focus pretty good.
Right.
So that really helps out.
Yeah. That's
there are a couple of questions in the chat. One is from Raina, and it's, how do you know what angle is necessary between the collimator and objective lens? And there's also a message from Brian Coville. He wanted to know your contact information for Douglas and Brian, but I guess you could do that over private message. But I was wondering if you could answer Raina's question about the collimator and the objective lens.
the collimator.
What angle is necessary between the collimator and objective lens?
About 52 degrees, if I remember right.
Yeah, generally, I assume he's meaning this sort of angle,
Yes,
right? There's a grating, and then there's a lens, and there's a
Exactly,
lens.
Douglas,
Right?
that's what I mean. Because this is a collimator and this is the objective. How do you know what angle to put?
Well, generally, you want to make that angle as small as you can. As it gets further apart, there can be optical problems. So, it depends on the size of the lenses and how you position them. It's a bit of a geometric problem. It tends to always work out to be about 30-ish degrees, I'd say. But you generally want to make that angle as small as possible. So, like, you don't want it 45. It gets tricky to make it below 35, I'd have to say. But you can usually get it down to about 30 to 35, I'd say.
So this could be more or less trial and error.
It's kind of a layout problem, as I said, if your lenses are bigger diameter, that has some advantages in terms of capturing more light and so on. But then it means you can't actually get them as close together.
Is there also a certain ratio between objective and collimator lens, or can you use any focal length there?
Actually, one thing I didn't mention was I believe that the longer the focal length of your telescope is, the longer the focal length of your collimator needs to be. And just by kind of trial and error, I found that a collimator will support a telescope of about 5.5 times its focal length. So, meaning if your collimator is 100 the millimeter focal length, it'll give good focus, or will collimate a telescope of about 550 millimeters. So that's why I've kind of, and a few other people, I think, they're using collimators like 125 to 150 because that will allow you to use a telescope of 600 or 700 millimeter focal length. The guy in Australia who he happened to have a 900 millimeter focal length telescope. I suggested that he probably needed a 200 millimeter collimator, and he took my suggestion. It seems to have worked. What happens is, if the longer the focal length of a telescope is, the bigger the image is projected on a slit, right? It'll be 5 millimeters big or something. And these simple lenses, like a simple doublet type lenses, won't image a very big image circle. I think a camera lens, like a Pentax lens, is built to image 35 millimeter film. It'll give a bit bigger image circle than a typical lens, but the longer the focal length is, the bigger that image circle seems to be. But the longer the focal length of this collimator is, the bigger the whole contraption gets and the heavier it is. So you probably want to keep it as small as you can for the telescope you plan to use. And the other lens, the camera lens, in theory, you just size it in order to give the right magnification so it fits on your camera sensor. Ideally, you probably want it as big an aperture to capture more light, but it tends to be not a problem. There's plenty of light even with a, like an f/5.6 lens.
So your ratio of 5.5 would mean for me that with 240 millimeter telescope, I am somehow limited in this case, or not? Because the collimator I bought from Shellac, the optical kit, as far as I remember, is 80 millimeter focal length.
Yeah, 80 is pretty short, and I think that's one of the limitations of that Shellac kit is actually the collimator lens is pretty small, but in theory it seems to work with about like this sort of 420 millimeter telescopes. It seems to.
But I have 240, so would that mean I would be better buying a 400 millimeter telescope or 460 millimeter telescope?
Your focal length is 240, so very short.
Yes. And taking your ratio 5.5, I would need a collimator.
Very small, right?
Millimeters.
Well, I mean, that's sort of, that's kind of a minimum. It'll support, the 80 millimeter collimator of the Shellac will, as I said, be fine for the telescope you're using. It's more than enough.
Okay, thank you.
Okay, thanks, Douglas. It's been really excellent to hear all of your work, and it's fascinating to see how you actually stack it and process it and see how it comes out. So thank you very much. Has anybody got anything further to say? Any other questions, any quick questions, and then we'll close up?
Well, I'll say one thing. If you're not working with spectroheliographs, they're very addictive. You can spend an awful lot of time just scanning the sun back and forth. So word of warning, it could become a very nasty habit. A good habit.
Well, I was about to say I was a bit undecided when we started, but I've changed. So begins another journey, I think. Douglas,
the most important thing I learned today was I was exposing wrongly my video files, because I saw at your video files, Doc, that you nearly overexpose everything until you get only the black line. And I was trying not to overexpose. Maybe that's why I'm missing some sharpness in my images.
That's certainly true for hydrogen, hydrogen alpha and beta. You have to overexpose it more than you think, right? Because you're only interested in the line, not things off the line. But I'd actually say for the calcium, it's a bit the opposite. You have to underexpose it because there's such bright contrast in the calcium lines that you actually have to make it darker than you think.
Yes, I noticed in the calcium, if I expose too much, the bright areas are totally burned out. So I tried lately to underexpose it a little bit. and not overexpose the details which are inside the black line.
Right, exactly.
Doug, I'd like to know, is your version of the software available?
Yes, yes, it is. It's on the GitHub. I'll send you an email. I've got your email, right?
Yes, you do.
Yeah. So, but I've posted links to the software at a bunch of different, forums and so on. But I'll send it to you. Or if you, as I said, it's to me a little more bare bones in a sense than Valerie's. She keeps on putting more bells and whistles into it, and ours is, we haven't done much to it since about last November.
Yeah, well, I just want to try the stacking.
Yeah,
And
yeah.
It sounds like your software is more
For
amenable.
stacking, because I think that Valerie never really put much effort into the whole stacking idea. But a few people, like there's a guy called Jean-Francois Pité, actually, who first kind of motivated me to do stacking, and he had a lot of suggestions. But if you did it this way, it'll all work out better for stacking. So he had a lot of like input into sort of methodology of how we did a few things.
Can I just jump in, Douglas, please? Mm-hmm. Yeah, when you stack, you have to stack several full disk images, and this will take some time. So I guess things are changing in the sun, or no?
Well, generally speaking, a single scan, right? If you're scanning at, as I said, maybe 16, 14 times sidereal, each scan takes about 15 seconds or so. Okay. You're only, if you really want to get a very good stacked image, I typically scan about 20 times.
So that will take what, 5 minutes? Or
yeah, it's about five. It's about.
So it's okay.
4 or 5 minutes. So some things are going to change, but it's not. Right. It's not a huge.
Not dramatic. Yeah.
Not very dramatic. At least, particularly at the resolution scales we're talking about. This isn't like 250
for the full disk. It's okay.
The millimeter aperture, right? This is like 100 millimeter aperture or so.
Thanks. Great presentation, by the way.
Thanks, Pedro.
I have to buy one, but I don't have a 3D printer. But can you buy one already?
I think you can. I think there are companies that sell the 3D printed parts.
Okay. Right. I'll check it.
I think most of them are in France.
Okay. I know most of these guys. Buil, I know Buil very well also. So
yeah, I think if you hunt around, there's a couple of French 3D printing companies now.
Okay.
Yes, in the page from Christian Buil, there is a link to a company sells the printed parts already, even with the brass insert already installed and everything.
Right.
One of the most difficult things was to adjust the grating so the total scan from the beginning to the end is parallel to the image. This is very, very critical, very finicky to adjust this. I don't know if you have seen my images of my Solex, which has now 3 focusers, more or less, camera, telescope focuser, and the grating motor. And this helps a lot to get good adjustments at the end effect. And the other thing is, as Doug mentioned, focusing the line is focusing the image in the video file. This is not very easy. Because of the turbulence, you would really need some time to find out which is the best focus on the sides of the spectrum. This can even demotivate you to keep going with the Solex. It's happened to me.
Alexandra, thanks for hosting this. And
yes,
what do you typically do with the recorded video?
I will post it in the Solarchat thread when it's finished and it's processed and it's uploaded. And then usually I leave the post up for a few days and then move all of the previous ones into, because I don't know where to put it, I just put it into the SPOD section so anyone can you know find it from there. But thank you very much, and I'll close up now, and I'm sure everybody loved it, so thank you very much for putting all this time and effort into it. It's been great.
Great. Okay, thanks a lot, guys, and thanks for joining.
Thank you.
Thank you
Bye.
very much. Bye-bye. Thank
Bye.
you. Bye-bye.
Bye.